This is SpaceTime Series 27, Episode 26, for broadcast on the 28th of February 2024. Coming up on SpaceTime, a new record-breaking black hole quasar, strong evidence that Supernova 1987A produced a neutron star, and Earth's first building blocks of life. How could they have survived the early planet's radiation? All that and more coming up on SpaceTime.
Welcome to Space Time with Stuart Gary.
Astronomers have discovered the brightest and fastest growing black hole quasar ever seen. Quasars are powerful beams of energy and matter generated by material being crushed and ripped apart in the accretion disk surrounding a feeding supermassive black hole. While most of the material in the disk will eventually pass a point of no return called the event horizon and then fall forever towards the black hole's singularity, some of the material gets caught up in powerful magnetic fields before reaching the event horizon. This material is then focused by the magnetic fields and fired out into deep space as beams or jets at superluminal speeds. Now, depending on the angle they're seen at, astronomers refer to these jets as quasars, blazars, or active galactic nuclei. These beams can be bright enough to be seen across on the other side of the universe, and they were the most distant objects ever detected prior to the arrival of the latest generation of telescopes. The newly detected quasar, called J0529-4351, is over 12 billion light-years away. A report in the journal Nature Astronomy claims the black hole has a mass of more than 17 billion suns, and it's growing by at least one solar mass per Earth day. The matter being pulled towards the black hole on its accretion disk emits so much energy that J0529-4351 is over 500 trillion times more luminous than the Sun, and that makes it the most luminous object in the known universe. Now, just a few years ago, NASA and the European Space Agency reported that the Hubble Space Telescope had discovered a quasar called J043947.08 plus 163415.7, which was as bright as 600 trillion suns. However, that quasar's brightness was being magnified by the gravitational lensing effect of a foreground galaxy. The actual luminosity of the quasar was more like 11 trillion suns. Not bad, but nowhere near as bright as this newly discovered one. As a general rule, the most luminous quasars indicate the fastest growing supermassive black holes. One of the study's authors, Samuel I from the Australian National University, says all of this light is coming from a hot accretion disk some 7 light-years in diameter, which is probably the largest accretion disk in the known universe. Now, to put that in perspective, 7 light-years is about 15,000 times the distance between the Sun and the orbit of Neptune. It's twice as far away as the Sun's nearest stellar neighbour, Proxima Centauri. And remarkably, this record-breaking quasar was apparently hiding in plain sight. In fact, the study's authors are surprised that it remained unknown until now. It turns out the quasar had shown up in images from the European Southern Observatory Schmidt's Southern Sky Survey dating back to 1980, but it wasn't recognised as a quasar until decades later. Finding quasars requires precise observational data from large areas of the sky. The resulting data sets are so large, researchers often use machine learning models to analyse them and to tell quasars apart from other celestial objects. The problem is these models are trained on existing data, which limits potential candidates to objects similar to those already known. So if a new quasar that's more luminous than any previously observed quasar comes about, the program rejects it and instead classifies it as a star not too distant from Earth. Even an automated analysis of data by the European Space Agency's Gaia satellite passed over the black hole as being too bright for a quasar, instead also suggesting it was probably a star. But Ley and colleagues identified it as a distant quasar using observations from the ANU's 2.3-metre telescope at the Siding Spring Observatory in far western New South Wales. Discovering that it was the most luminous quasar ever observed, however, required a larger telescope and measurements from a more precise instrument. And that's where the X-Uta spectrograph on the European Southern Observatory's Very Large Telescope in the Chilean Andes came in. Lai says finding and studying distant supermassive black holes could shed new light on some of the mysteries of the early universe, including how their host galaxies form and evolve.
We did our study scanning 80% of the whole sky looking for bright quasars, and we found one unexpectedly at the highest redshift, that is the furthest away quasar that was found through our selection method, and this was J0529-4351. And so we took additional measurements, of course. We took some Australian instruments on the Siding Spring Observatory in Coonabarabran, and so we looked at it through the ENU 2.3 meter telescope and the SkyMapper survey telescope, and we also used an 8-meter class telescope in Chile called the Very Large Telescope. We collected additional data in order to make more precise measurements.
What do we know about it from the measurements you've taken?
Yeah, our best estimates of the black hole mass, that is the black hole in the middle of the quasar, that's what's powering the high radiative output from this object. So this black hole has a mass of about 17 billion solar masses, and it has a luminosity output that's maybe 500 trillion times the luminosity of the sun. That is, you could put this object at about 100 parsecs away, so much further away than the closest star, and that would be about more than 300 light years away, and this object would still shine as brightly as the sun in our sky. So this is an incredibly bright object with a stupendous radiative output that is clearly beyond our human comprehension.
When you guys discovered this thing and you realized that it wasn't a nearby star, it was actually a quasar 12 billion light years away, how'd you feel?
Yeah, I mean, it was pretty incredible because through our selection study, when we were looking for bright quasars in all sky really, but we found a lot of new ones in the southern sky because it's less well studied. We were mostly looking at closer quasars. Most of the new quasars that we found were lower redshift, that is, they were closer to us. But one object popped out, and it was an object that's at a redshift of 3.963, roughly there. And it was really incredible because we never expected to find an object that far away through our selection. And so it was really a slap in the face kind of moment. And, science happens not by eureka moments, but also by what? Is this correct? Sort of moments. Because we really needed to make sure that our estimates were correct and to confirm our findings.
So you double-checked and triple-checked and checked again and got somebody else to review?
Exactly, yes, yeah. More than one person. I mean, we published it in Nature.
The size of this thing, the accretion disk itself is what, 7 light years across?
Yeah, that's right. If we take our extrapolations of how large the accretion disk must be in order for this luminosity, then we will find out that this guy is 7 light years across, and each light year is 9 trillion kilometers. So this is an absolutely massive accretion disk.
Twice as far as the nearest star.
That's exactly right, yeah.
Other than the sun, I mean.
Yes.
This is part of a larger survey, you were saying?
Yes, this is indeed part of a larger survey where we found over 100 newly discovered quasars. So the survey is called ALBRIC, or All Sky Bright Complete Quasar Survey. So work that we've been doing in all of the sky, and 80% of the sky we've been scanning, and we've developed a novel method for distinguishing these quasars from a lot of stars. So we're in the era of very large data sets in astronomy, so we need to come up with more clever ways to characterize and classify these objects. This quasar was missed in the past because now that we have so much data, we usually run the data through perhaps artificial intelligence or other sorts of classification algorithms. And because of the brightness of this object, it was originally misclassified as a star.
And so what, it took humans to make the final determination because of that?
Yes, so it took us to come up with a different method that's different from what everyone else is using in order to pick out this object as a potential quasar candidate.
Are you surprised that there is something so big, so far in the early universe?
Yeah, I mean, it is surprising in a sense, but the universe is very large, and we have found very extreme objects that are very far away. And this has caused a sort of tension in the black hole community in the sense that some of these black holes are so large, so supermassive, that we're not exactly sure how they formed. The best way that we know that these black holes, or any black hole forms in general, is the collapse of a massive star. But even if you allow for all the time in the universe, by the time that we observe these kinds of objects, for them to continue to accrete mass, or continue to grow by feeding on matter from its accretion disk, there might still not be enough time for these objects to get to the size that they were observed at. So there's a bit of a tension in the community, and that we've come up with a lot of other solutions for how you might be able to form these massive black holes.
So if it's not population 3 stars that are doing it, these things must be forming directly out of the collapse of the same gas clouds that form galaxies.
Yes, very, very possible. So a collapse of supermassive stars, direct collapse of clouds of gas without fragmentation, and these are possible to form black hole seeds. We call them seeds from which these black holes continue to accrete from. And these seeds can be 10 to the 4 or 10 to the 5, so solar masses.
And that's always been one of the big debates, hasn't it? Which came first, the black hole or the galaxy around it? Well, this tends to, at least there's evidence now with this sort of thing that the two are forming together in unison as part of a single process.
Yes, that's exactly right. And in the community, the last couple of years has mostly been dominated by studies which estimate that the galaxies form first and then the supermassive black hole. But more recently with JWST and other results like these ones, we're thinking that maybe in some certain cases that these black holes could have formed first and become a seed for the galaxy. So this is a classic chicken and egg problem, which one came first. And the most recent evidence are of these overmassive black holes. That is, the size of the black hole is roughly the same mass as all of the stars in that galaxy. And this is off of our normal relations that we can apply in the local universe.
So where to next with this discovery?
So the next thing that we'd like to do is we'd like to use the Very Large Telescope's gravity instrument. And so this instrument can go down to arc-second or milli-arc-second angular resolution. And this is useful so that we can resolve the material that's orbiting around the black hole. So we can directly see this material that's orbiting and investigate the dynamics of that region. And this will give us an even more precise measurement of the black hole mass. We've taken spectra of this object with an ANU 2.3 meter telescope.
Oh, what did you find?
Yeah, so we split the light through a prism or a grating, and what we find when we split the light into its various wavelengths, the surprise was that even with the optical instruments in the ANU 2.3 meter telescope, we could see the Lyman alpha line clearly in the center of our wavelength coverage. And so that indicates this object is very high redshift, and that was the biggest surprise to us because this object was so bright. But it is in fact so far away that the light has traveled 12 billion years to reach our instruments.
Now that you've seen this thing and you've been able to quantify it, well, what sort of experiments are you hoping to do?
One of the most exciting things that I think that we can do with ultraluminous quasars like this one is something called the Sandwich test. This means that as the light from the quasar, if you think of it as a distant beacon, like a lighthouse from the early universe, as the light travels through the cosmos on its way to us, it passes by lots of neutral hydrogen gas. And this gas absorbs the light and creates what's called the Lyman alpha forest. So this creates a lot of absorption lines past Lyman alpha, so at bluer wavelengths than Lyman alpha. And so what this does is you can get a lot of redshift estimates. And so in the future, and it may even be decades in the future, when we finally have these extremely large telescopes or 30-meter class telescopes, we can look at these bright quasars such as J0529, and we can look at the Lyman alpha forest to get a ton of redshift estimates. And all of these redshift estimates, we can continue to observe this object year by year and look at how these redshifts change. And what we're actually seeing there is a change in the redshift by year, is we're seeing the universe expand in real time. And we can use this quantity to look between different models of the universe and estimate which one is the most appropriate model of our universe's expansion.
Well, there are tensions regarding the Hubble constant now, aren't there? So this will help.
Yes, exactly, yes. This will help with the Hubble tension, this will help with our cosmological models, and this will help in general with our understanding of how the universe behaves.
That's Samuel Lai from the Australian National University. And this is Space Time. Still to come, new evidence that Supernova 1987A produced a neutron star, and Earth's first building blocks of life. How could they have survived the early planet's radiation? All that and more still to come on Space Time. Okay, let's take a break from our show for a word from our sponsor, Incogni. In today's digital age, your personal information is more valuable than ever. No matter what you do, you simply can't hang on to it. It's sold on in shadowy online markets without your consent, and that means your privacy is a constant risk. But there is a light at the end of the tunnel, thanks to Incogni. With Incogni, you have the power to reclaim your privacy. You see, Incogni is your champion, navigating the complex shadowy web of data brokers out there to ensure your information is deleted and your privacy protected. However, the path to privacy is not an easy one. There are data breaches happening all the time. You hear about them on the news every day. And the manual effort to track down your personal information is a daunting, nearly impossible task. your name, your social security details, your driver's license, your registration papers, even your home address and your online activity. They're all out there and they're all at stake. And that's where Incogni comes in. It's tirelessly working to track down your data and keep it safe from prying eyes. With Incogni, you're not just signing up for a service, you're securing a guardian for your personal information. The Incogni team's constantly monitoring and acting to ensure your data remains yours alone. And as a special offer for SpaceTime listeners, we're giving you an exclusive 60% off the Incogni service. And of course, that comes with a 30-day money-back guarantee. So why not protect your privacy by visiting incogni.com/StuartGary. That's incogni.com/StuartGary. Don't wait for your data to be compromised. Take action now. Go to incogni.com/StuartGary. And of course, we've included the URL details in the show notes and on our website. Protect your privacy. Go to Incogni. And now, it's back to our show.
You're listening to SpaceTime with Stuart Gary.
The long-running debate over whether supernova 1987A formed a neutron star or a black hole may finally have been resolved, with new observations from NASA's Webb Space Telescope finding clear evidence for emissions from a neutron star at the center of the supernova remnant. Supernova 1987A marked the explosive death of a spectrotype B3 blue-white supergiant star called Sanderluke 69202, which was located on the outskirts of the Tarantula Nebula, 168,000 light-years away in the Large Magellanic Cloud, a dwarf galaxy orbiting the Milky Way. The progenitor star is estimated to have been around 20 times more massive than our Sun. Light from the supernova reached Earth in February 1987, making it the closest observed supernova since the invention of the telescope and Kepler's supernova, which was visible from Earth in 1604. 1987A gave modern astronomers an opportunity to study a core collapse Type II supernova in unprecedented detail, gleaning many new insights into stellar evolution. Now, based on the mass of the progenitor star, supernova 1987A should have produced a super-dense compact stellar corpse called a neutron star. And the neutrino data suggested that a compact object did indeed form at the star's core. The problem is astronomers weren't able to confirm its existence because it lay hidden, concealed by a thick cloud of cosmic dust and stellar debris. You see, the supernova explosion that took place at the end of this star's life resulted in a huge amount of gas with a temperature of over 1 million degrees. But as the gas began to cool down, it quickly crashed to below 0 degrees centigrade, and some of this gas then condensed into solid dust grains. The presence of this thick cloud of dust has long been the main explanation as to why the missing neutron star hasn't been observed. But many astronomers were skeptical about this, and they began to question as to whether or not their understanding of stellar life cycles was correct. And that's where the new Webb observations come in. They mark the first time that the effects of high-energy emissions from a probable young neutron star have been detected. About 2 hours prior to the first visible light observations of supernova 1987A, 3 observatories around the world detected a burst of neutrinos lasting for about 10 seconds. That's the amazing thing about supernovae. Although they shine brilliantly right across the electromagnetic spectrum, they actually shine even brighter in neutrinos. And because neutrinos are so weakly interacting, they pass through the remnants of the star without any hindrance, so they get here much quicker. The 2 different types of observations, electromagnetic and neutrino, were linked to the same supernova event and provided important evidence to inform the theory of how core collapse supernovae take place. Of course, indirect evidence for the presence of a neutron star at the center of the supernova remnant's been around for the past few years. And observations of much older supernova remnants, such as the Crab Nebula, have confirmed that neutron stars are often found in supernova remnants. However, the study's lead author, Clarice Franson from Stockholm University, points out that no direct evidence of a neutron star in the aftermath of supernova 1987A had been observed until now. The Webb Space Telescope began scientific observations in July 2022, and it turned its focus to supernova 1987A in the same month, making it one of the first objects observed by Webb. The authors used Webb's medium-resolution spectrograph on the mid-infrared instrument to study each pixel, allowing them to see spectroscopic differences right across the object. An analysis of the Doppler shift of each spectrum also permitted the evaluation of the velocity of each position. A report in the journal Science claims spectral analysis of the results showed a strong signal due to ionized argon at the center of the ejected material which surrounds the original site of Supernova 1987A. And subsequent observations using Webb's near-infrared spectrograph at shorter wavelengths found even more heavily ionized chemical elements, especially 5 times ionized argon, meaning argon atoms that have lost 5 of their 18 electrons. Now, doing this requires energetic photons to form, and those photons have to come from somewhere. Franson says it's clear that there needs to be a source of very high-energy radiation at the center of the supernova remnant in order to create the ions observed in the ejector. And the only scenarios likely to cause this all involve a newly born neutron star. This is SpaceTime. Still to come, Earth's first building blocks of life. How did they survive the planet's early radiation? And today's February the 28th, which means tomorrow is February the 29th, making this a leap year. But why is it so? All that and more still to come on SpaceTime. A new study has been looking at how the first building blocks of life survived the radiation of the early Earth. The authors speculate that cell-like structures containing specific antioxidants resistant to radiation could have allowed some of the earliest building blocks of life on Earth to survive the harsh conditions. Early Earth is known to have much higher gamma radiation levels than it does now, which means that the first signs of life would somehow have had to survive and grow under levels of radiation which we couldn't survive today. A report in the journal Nature Communications shows how researchers developed a model of a protocell, a likely ancestor to cellular life, containing polyphosphate and manganese ions, and exposed it to high levels of gamma radiation. The researchers say their protocell model stayed intact while other models without the manganese ions were destroyed. And that suggests that manganese antioxidants could have been part of the mechanism protecting these building blocks of life. This is SpaceTime. Still to come. Tomorrow's February the 29th, which means it's a leap year. But why is it so? And later in the science report, biologists discover 2 new animal species in the Australian outback. All that and more still to come on SpaceTime. Well, today's February the 28th, which means tomorrow's February the 29th, and that makes this year a leap year. Many people know that February gets an extra day during a leap year, but often they don't know why. Leap years play a crucial role in aligning our calendar with Earth's orbit around the Sun. The orbit, otherwise known as a tropical year, takes about 365.24 days to complete, and this is slightly longer than our standard calendar year of 365 days. This extra quarter of a day each year may seem insignificant, but over time it all adds up, leading to a noticeable shift in our calendar. Without adjusting for this extra day, our calendar would gradually fall out of sync with astronomical seasons, causing a significant drift over the years. And so to alleviate this problem, leap years are added to prevent this drift and maintain the alignment of our calendar with Earth's journey around the Sun. To counter the misalignment, the leap year system adds an extra day to the calendar every 4 years, and the adjustment is made by extending February to 29 days. But it's not that simple. The seemingly simple solution of adding a day every 4 years had to be further refined in the Gregorian calendar, the most widely used calendar system today. Leap years were incorporated as far back as Roman times, when a year was separated into 12 months lasting 365 days. But back in the year 46 BCE, Emperor Julius Caesar proposed a new Julian calendar, which would add an additional day to the shortest month of the year, February, every 4 years, in an attempt to allow for a predictable correction of the issue of the quarter-day drift. However, this is actually a slight overcorrection of the problem. See, the solar year isn't 365.25 days, but in fact slightly less, 365.2422 solar days. And so the Julian calendar and the solar year were still drifting apart, although at a far slower rate of 11.2 minutes per year. By the late 1500s, the small overcorrection in the Julian calendar had accumulated to a drift of 13 days with respect to the solar year. And that's where Pope Gregory XIII comes in. In 1582, he gave us the Gregorian calendar, which modified the Julian calendar to account for the 11.2-minute drift. To improve upon the overcorrection made by the Julian calendar, the Gregorian calendar skips 3 leap years every 400 years. This gives an average year of 365.2425 solar days, which is much closer to the solar year of 365.2422 solar days. Then, of course, there's the issue of leap seconds, but we'll deal with that on another occasion. This is SpaceTime. And time now to take another brief look at some of the other stories making news in science this week with the Science Report. A new clinical trial may have found the answer to people forgetting to take the hypertension medication on time after it showed that a single injection of a new drug called zilebesiran can significantly lower blood pressure for up to 6 months. The drug works through RNA interference, which is when small pieces of RNA stop proteins from being made by binding to the RNA that codes for those proteins. The study found that doses of 150, 300 or 600 milligrams every 6 months, or 300 milligrams every 3 months, were able to decrease blood pressure at 3 and 6 month intervals compared with a placebo. The findings, reported in the Journal of the American Medical Association, suggested the drug could effectively treat high blood pressure with injections 2 or 4 times a year. Scientists have discovered 2 new animal species in the Australian outback. The findings, reported in the journal Molecular Ecology, claim scientists have discovered the aptly named delicate mouse is actually 3 separate species. Researchers from the Australian National University and the CSIRO made the discovery during detailed genetic testing of the small native rodent. The delicate mouse is a range stretching from the Pilbara region of northern Western Australia across parts of the Northern Territory through Queensland and down to the northern New South Wales border. The authors admit it can be difficult for the untrained eye to tell the 3 species apart. That's where the genetic testing comes in. The new discovery will provide a significant boost for future conservation efforts for the tiny mouse. A new study has shown that even over the COVID-19 pandemic, people remained fairly consistent as to whether they believed in conspiracy theories or not. The findings, published in the journal Scientific Reports, are based on new research looking at the conspiracy beliefs of nearly 500 New Zealanders and Australians over 6 months during 2021. Notably, the number of people who started off agreeing with a conspiracy theory but later changed their mind were offset by a similar number of people going the opposite way. Apple have issued a warning telling people not to use rice to dry their wet iPhones. With the details, we're joined by technology editor Alex Zaharov-Reutt from TechAdvice.life.
Apple is warning that you should not dry your iPhone in rice, even though rice is known to suck all the moisture out. And look, both Samsung and Apple will say that their devices have water resistance up to a certain depth for a certain number of minutes, but neither of them will actually say that their devices are completely waterproof. And in fact, I had a Sony device that was marketed as being effectively waterproof, and I remember putting it into a jug of water, not even very deep, like 30 centimeters worth of water. And when I took it out, even though the phone was being marketed, that was the end of that, yeah. And look, Sony replaced it for me. Very nice of them, but they don't sell the Xperia devices in Australia anymore, and they had ads showing people swimming underneath. So it's one of those things where just because a device says it's waterproof.
Yeah, I've been to the Samsung store in George Street in Sydney, and I've seen their Galaxy sitting there at the bottom of a little aquarium, and quite happily.
Yeah, and that's because it can theoretically do that for 30 minutes or 60 minutes. They don't want to warrant it for longer than that because it's meant to survive a quick dunk into some water. But really what happens is on your iPhone, you get a warning message telling you that there is moisture in the Lightning or nowadays the USB-C port. And if you see that message, Apple wants you to not plug the phone into the cable because that obviously can zap the phone should it try to charge whilst it's wet. And you would think that putting it into rice, which people have done for years, would be a good thing. But Apple is saying don't do that. And the reason they give actually is weird. They say that there could be small particles of rice that could go inside the connector, which could damage the phone. It's the right
size for rice, isn't it? Yeah.
Well, theoretically it is. And they're also saying, interestingly, don't use an external heat source or compressed air. So don't get the hairdryer or a heater to try and force it to dry. Don't use compressed air because I presume you could force the water inside the phone. And they're even saying don't insert a foreign object such as a cotton swab or a paper towel into the connector.
Yeah,
so really this is about the connector.
Department tell me the same thing, but we won't go into that now.
What they're saying is that you should allow the phone to dry out naturally. I mean, Mac Daily News said, let it dry out for several hours longer than you think it should be dried for. If you keep seeing the message that your iPhone connector is wet, then contact Apple. I mean, you can also try using a different cable if it's working, doing that with one cable and not with others. And look, the best thing to do is to go to an Apple store if you suspect there's real water damage. There's those phone kiosks as well. The best thing is to avoid water altogether.
Now, I had a problem with my iPhone. The screen wouldn't turn off after a set period of time that I had set for it. And you told me to make sure it's updated, and that worked.
Well, that's right. Look, phones and devices are supposed to update automatically.
Yeah, mine's
Apple
set
doesn't.
for that.
Yeah, the devices don't all update at the same time, because if there's a problem, then Apple or Microsoft or whoever has a chance to find out what the problem is and fix it before hundreds of millions of other devices are affected. But also, Apple has 1 billion active user accounts. If 1 billion devices all hit upon Apple servers at the same time, it would cause a distributed denial of service attack, or basically something that replicated that, even though they were all custom. So it's always a rollout. Nothing stopping you as an individual from checking for those updates manually. And I'm warning people every few weeks that the new update is out and to check, because I know that you cannot always wait. And usually on iPhones and iPads and Macs, if there's a problem, and unless it's a physical hardware problem, usually an update will fix it. Whereas on the Windows or potentially even Android side of things, there can be some sort of malware or adware or something at play that can be causing problems.
And what's happening with your show on TNT this week?
This week I'll be speaking to a telecommunications expert, and I've got a big announcement which will be at my website, techadvice.life, and it's to do with mobile communications. And this is quite revolutionary. It's happening more or less in the same week that the Mobile World Congress is happening in Barcelona. And this is not being showcased there, but it's going to be, in one sense, more interesting than a lot of the other announcements combined. So definitely check out my interview on TNT and check out my website to learn more.
That's Alex Zaharov-Reutt from TechAdvice.Life. That's the show for now. SpaceTime is available every Monday, Wednesday and Friday through Apple Podcasts, iTunes, Stitcher, Google Podcast, Pocket Casts, Spotify, Acast, Amazon Music, Bytes.com, SoundCloud, YouTube, your favorite podcast download provider, and from SpaceTimeWithStuartGary.com. SpaceTime's also broadcast through the National Science Foundation on Science Zone Radio and on both iHeartRadio and TuneIn Radio. And you can help to support our show by visiting the SpaceTime store for a range of promotional merchandising goodies, or by becoming a SpaceTime patron, which gives you access to triple-episode commercial-free versions of the show, as well as lots of bonus audio content which doesn't go to air, access to our exclusive Facebook group, and other rewards. Just go to SpaceTimeWithStuartGary.com for full details. And if you want more space time, please check out our blog, where you'll find all the stuff we couldn't fit in the show, as well as heaps of images, news stories, loads of videos, and things on the web I find interesting or amusing. Just go to SpaceTimeWithStuartGary.tumblr.com. That's all one word, and that's Tumblr without the E. You can also follow us through @StuartGary on Twitter, @SpaceTimeWithStuartGary on Instagram, through our SpaceTime YouTube channel, and on Facebook, just go to facebook.com/SpaceTime with Stuart Gary.
You've been listening to SpaceTime with Stuart Gary. This has been another quality podcast production from Bytes.com.